Welcome back to my Commodore 64 Memories videos. This is where I look at old Commodore 64 software and some of the technical details behind them. Today we have Leaderboard World Class Golf, released in 1987 by Access Software, created by Bruce Carver and Roger Carver. I had this game on the disc version way back in the day, and I used to play this an awful lot with my dad because he also liked golf. We used to go play golf sometimes, real golf, but not very often. Didn't get out very much, but we used to play this golfing game quite often on the Commodore 64. I noticed the turbo loader, the disc turbo loader, doesn't really enable the screen, so you don't get to see this lovely loading screen in the background. It seems to load it anyway in the background, but with the screen off, but we can see it in the debug graphics map there in ICU 64, but it never really displays on the Commodore 64 screen, and then it just asks for the next side of the disc, which I'm going to insert now. This game then goes into the leaderboard title screen, which asks for the number of players, so you never really see the loading screen with the disc turbo loader enabled. A bit weird. This game also needed a dongle, and the dongle connected to the tape port. But because I had a tape unit as well as a disk drive, I actually just pressed play on the tape unit, and that meant that I didn't need to install the dongle. So I'm guessing that the dongle asserts the tape play sense signal, and then the game checks for that in the background. I'm not really going to look for the dongle protection code in this version, but you'll notice that I've got the tape button pressed in the emulator. So now the game loads. I really want to have a look at the rendering for this game. I want to have a look at what it's doing for the sprite animation, and maybe I also want to try and decode the course data, or the hole data rather. I think each hole is loaded from disk for each hole that you complete. So I've just started this game. I think I started it in kids mode, right, which is the easiest mode. You don't have to worry about the slice of the ball veering to the left or to the right, slicing it and hooking it, if I remember my golf terminology correctly. You also don't need to worry about the wind, if I remember correctly. So we've got this rather nice top-down view. We're going to be using this cycle between the top-down view and the 3D view to try and debug a little bit about the 3D rendering, I think. So we can see, wow, straight away we can see, look, there are animated dynamic sprites there used for the golfer's animation. Not a surprise, because the golfer animation actually has a large number of frames. Too many, I think, to fit inside memory without some kind of compression. Looks like they're being decompressed. And of course, the game uses a multicolor bitmap mode for rendering. Let's do a watched store point memory breakpoint for the sprite data in memory, and we can see, okay, so this looks like a clear, so it's clearing a whole sprite's worth of data, actually probably a little bit more. We'll check that maybe. But yes, that seems to be a clear loop. So let's, yeah, that's clearing 6800. So let's step over that, and then let's see if we can get to where it's copying data from somewhere. So we'll hop out of that routine. We'll then reset the watch store point over that memory range for where the sprite data frames are being displayed from in memory by the bit chip. Actually, that looks like the golf ball, doesn't it? If I do the ms command, which displays the memory sprite, or the sprite memory, rather, at that address. Let's keep on going, because I think it's just displaying the ball and the cursor. Let's see if I can find the precise memory for the player, probably the player's legs, right, or the arms, or whatever it is. It's it looks like a few high resolution sprites stacked on top of each other as well. That's what gives this game this really nice, distinctive, detailed look, right? Is that you've got this high resolution golfer animation on top of the lower resolution multicolor bitmap. So anyway, there we go. Okay, so it's clearing that data again. Okay, that's fine. We'll just make sure that we'll just put a breakpoint on the first byte of that first animated graphics character. Ah, there we go. Look, it's loading indirected from F7, Y, and then storing it into 6800, X. So that looks like it was copying in or decompressing some data into that sprite frame there from F7, F8 indirected, and then that's the clear. Okay. Yep. So the golfer frame is animating. So we'll have a look. Yeah, it's copying what looks like compressed data from 764A onwards. 764A is basically this kind of like randomish data there in memory. Look, it's this part of memory here. So it looks like it's decompressing, copying dynamic sprite animation frames from that area in memory there into the sprite memory where the VIC chip can actually display it from. Okay, that's cool. So high resolution dynamic sprites for the golfer animation. Really does look very nice, doesn't it? If I fill a good chunk of memory there, 7,000 to 7,800 there, if I then let the golfer animation play, let's see what we get on the screen on the real Commodore 6. Yeah, there we go. All of the frames have got corrupted when the golfer swings their club. So we'll load back the snapshot again, so now we know that those are the compressed animation frames in memory. I say compressed because they look like random gibberish, right? The VIC chip is, or the graphics map decoder view doesn't display them as correct looking sprites. It looks like randomish data. So kind of randomish data tends to indicate some level of compression. Okay, because you're removing blank areas of memory and you're removing repeated bytes and you're trying to compress it up. In the machine code monitor, let's use the list command to list the directory contents of the disk. Now, I want to try and understand the coarse rendering and also the coarse data. So I think the RNG file is the range, the driving range of the whole. The DMO file, I think, is the demo hole that the game uses when it's doing its self-playing demo. So because I've entered the range by pressing R, I think it was, on the keyboard on the title screen, then it goes into the driving range, which is great because it's a small, not very complicated hole that we can try and debug, right? Because we want some kind of simpler data so that we can track differences in the view when we're trying to understand the coarse data and understand the rendering of the graphics on the game. So I need to know what's inside this RNG file that's been loaded. Let's use my tweaked version of C1541 so I can use the same command, a list, and there's the RNG file there. Let's show the blockchain for the RNG file. So track and sector 31 and 1. So let's bpeak command. So that's the track and sector, next track and sector. Then there's the low byte, high byte of the start address of the file. So that's C554. Okay, well, let's have a look at C554 in the game's memory and see if we can spot any data similar. Well, there we go, straight away. The RNG file is still loaded into memory with those identical bytes there. So 02000004, 020004. Yep, that a superficial look at the start of the data in memory seems to show matching bytes, right? So I think we can safely say, pretty much with a high degree of confidence, that the RNG file is loaded into memory at C554. So I think that we can start to understand the level data in memory. Now, let's have a quick little look at this. So we seem to have some low byte values here. We've got 4 of something maybe, and 2 of something else. And then we've got, what is it? A of something and 2D of something, maybe. Then we've got 00C6, D, C6, 0, C6, 0, C6. Those look like low and high bytes of memory addresses inside this approximate block of memory, right? C600, C60D, C600. Those do look like low-high memory addresses. Okay, so maybe some numbers of things or types of things followed by a bunch of low and high memory addresses as a table. I think that's what we can deduce from this by inspecting the data in memory to begin with. Now this range, this driving range hole is actually really simple. It's got what looks like 2 areas that get filled with green, which is the fairway, basically, right? The fairway in golfing terminology. And look, the game renders the furthest one first, I guess, but it's rendering it with a yellow outline. We can see the yellow outline starting to get rendered in the real C64 view, but the graphics map view shows more lines, more information, and that's because it doesn't have to cope with the VIC refresh as it progresses down the screen. So that's why, and because the yellow line draw takes so long, it looks like it's drawing halfway through the frame. So it looks like it takes a couple of frames to just draw the yellow lines. So anyway, let's draw into the debug graphics map view there. I drew some yellow outlines, and we can see, look, well, okay, so we can start to understand the code straight away. Look, this area of the code here seems to be fill an area, fill with color, right? So we'll add a label of fill with color to 31F9, and that's because I stopped and entered the machine code monitor as it was doing the flood fill. So then when we exited this subroutine and we get back to here, we know that that JSR to that memory address is filling with color green. So we'll just put a label there so we can understand the routine, the disassembly a little bit better. I'm going to be putting these labels and my findings into my debugging notes text file, and of course I will, as usual, be committing this text file to GitHub so you can also follow along and also use this information if you like. It's free and open for use. Anyway, so let's keep on stepping through this routine. I'm doing step over mostly. I don't really want to go into subroutines. I want to find the main draw routine, right? And usually the main draw of a game is usually a whole bunch of JSRs all up together. So I think after it fills in the area, it then draws green lines over the bounding yellow line. But you'll notice that when I drew the box of pixels into the debug graphics map view, the flood fill hasn't actually flood filled everything. It seems to be not a complete flood fill. It's missed out the right hand portion of the screen area, hasn't filled it with green. This is kind of important. It tells me that it's not doing a polygon fill. It's doing a kind of like a naive flood fill, which it basically seems to assume that it's filling a convex space. But of course, because I painted a whole bunch of pixels as a filled square in the middle, it's no longer a convex area. It's got a hole punched out of the middle of it, so it's not filling it completely. Okay, so it's not a recursive, like, full flood fill, it's just doing a naive fill, which is cool. So it's probably filling from a certain point within the middle of the polygon, perhaps, or from one of the vertices. Anyway, so stepping through this code a little bit more, I can start adding labels for observed effects on the screen, right? Especially in the debug graphics map view there. I saw that it was drawing and filling a green area. Aha! Look, this is what I was looking for. This looks like the main game rendering loop and probably gameplay loop as well. So there's a jump, and the jump seems to signify an entry point. Just after the entry point, there's a JSR there, there's a JSR there, and then there's a little bit of memory manipulation with the load accumulator D11,X there. But we'll put some breakpoints there, and we'll just advance over these JSRs, and we'll see what we can find on the screen, right? So there's a lot of memory access going on in the debug memory view when I jump over some of these JSRs. What should we do? Let's see. I think that routine there, AD5F, drew all of the trees in the debug graphics map view. So we'll label that with draw trees. The JSR before it is probably a calculation loop, but we'll have to delve into that in some more detail to understand the code properly. So I'm just stepping over the last few JSRs, and at this point it hasn't exited from that JSR yet. So I think that the Commodore 64 is waiting for me to press the fire button to hit the ball. So I think 1A0F is the main game logic loop, right? So we'll add a label for the main game logic loop as well. So adding labels in the Vice Monitor debugger window here allows us to more easily see the structure of the disassembly, because the disassembly view will also show the nice labels. And this is going to be useful because when we can see the higher level structure of the code, it's easier to understand the logic of what is happening at certain points when the code is trying to access certain memory. And then from there on, we can hopefully understand the course data. So we're back at the beginning of the loop now. I've gone into the overhead view and I've gone back, or trying to go back to the 3D, T view, which is, or rather from the golfer, behind the golfer view, rather than the overhead view. The overhead view doesn't seem to use this main rendering loop. It might be using different code or reusing some parts of the code. But yeah, we're going to go back to the 3D view from the overhead view now. Basically, 2941 seems to be the main entry point for going back to the 3D view and starting to render the 3D view. Starting to render again, let's disassemble 20AA code. Look, there's a load X followed by a bit of an absolute address, followed by another bit of an absolute address, and then a store X. But look at these memory addresses here. 20AA, 20AD is very, very similar. It's in the middle of this startup. Look, there's a different load X value. Okay, so it's using the absolute bit instruction to skip the 2 bytes from the next load X. If you're really, really short of memory, this is a trick that you can use to have almost the same entry point for a function or a routine, but to skip over the first, say, instruction or so by using bit. This basically allows you to have different load X values with immediate values, and then continue the execution of the code. So 20AA, 20AD, 20B0 are very similar entry points for the code, just with different load X immediate values. But it enables the rest of the code to be reused. It's a little memory saving trick that I see often actually in 650 to 6510 code. So let's step, 1D77, that routine there, cleared the screen, drew the trees in the background, and then drew the clouds. So we will just label that as clear screen because that's basically what it does. It also seems to redraw a bunch of stuff as well, but basically it's clearing the screen. Stepping over this routine there to EA5, and it drew all of the green areas, the fairway and the tee and everything like that of the course. So we'll add a label for that. So to EA5, render. Render what? Render green areas, I guess. All green. Okay. So that's starting to render the hole. Is there a better label name for that? No, not really. So we'll put that in the debugging notes text file as well. Let's continue stepping over these routines one by one. Stepping over doesn't go into the routine, it just runs the routine and then goes to the next JSR instruction. So I'm looking for differences on the screen, especially differences in the debug graphics map view there. And one by one, if we step over, okay, and then that draws the trees, right? So if I step over that, it will draw the trees again. We know that it draws the trees, and then draw the T markers. We know that that does the T markers. Okay, let's go into this in a little bit more detail. So I've exited out and I've started playing a real hole rather than the driving range. So we've got more detail now in the hole, a lot more trees, more green areas, some sand traps as well, those bunkers, those yellow areas there. And the reason for this is because the driving range doesn't have water, doesn't have bunkers, sand traps. So we need this information to be able to try and understand different areas of the code. So we can add more labels to the main game rendering loop, right? So now that we've got this view here, we know that we're going to be getting some bunkers on the right-hand side. We can see those 3 bunkers there, roughly 3, I think. So let's step back into the code. We can look at it from the top-down view. We can look at it in the 3D view, right? But we need to start setting a breakpoint at the beginning of that render loop. So we'll do it when we're going back into the 3D view, right? So there's that breakpoint at 2941. We step over the clear screen. Now look for changes in the graphics map, debug graphics map view there. So we render green should render all of the green areas. Let's see. It's loading from 2183, storing it into 45. Yeah. Draw fill green. There we go. There's a routine that we understood just now. And there's an RTS there. Oh, look, this looks like very similar code, right? So there's one routine there, and then an RTS, and then another routine at 2EBA. Okay, I bet that's going to be doing some drawing, right? 2C56, 2C7. Yeah, I think it looks pretty similar code, right? But it's not being called, or we haven't understood it yet because we haven't added a label yet. So if we step over this JSR, look, it's drawing, filling the green areas one by one. So there's what? A certain number of iterations through that loop, right? It's like 1, 2, 3, 4, 5, 6, maybe 7 chunks. Okay, so then we're back to the main game rendering loop. Oh, look, 2EBA rendered the brown outlines for the bunkers, the sand traps. So we'll add a suitable label for that too. So let's render all, I don't know, render all brown. We'll call it that. To begin with, anyway, we might change the label name later on. But look, the same label name is called twice. The same routine, render all brown, is called twice in the rendering loop there with some different JSRs in the middle of it. Okay. So that tells me that there's some reuse of code, but the code is drawing differently colored things during the level. Okay, so maybe 2ED1, that was filling in the yellow area, right? So it was filling in the yellow area above the brown bit. So the sand traps, the bunkers, have like the brown area indicating that there's a kind of like the earth hole that the sand trap lives in, right? So it's lower down than the green area, than the fairway. So that's why it's just got, like the brown area, the earth area around the edge of the bunkers. So 2233 seems to be doing a lot of pulling from memory and storing into memory just before drawing the tree. So I think it's tree calculation. Right, so we'll put a tentative label in there for the tree calculation. So now if we go from the top-down view back to the 3D view, we can start to see that that main game render loop actually has a few labels now populated, and we can understand a little bit more about the whole code. So now we've understood in broad high level terms what the different portions of the code do. Let's see if we can test these assumptions by going a little bit closer to one of the bunkers. I want to try and trap or break into the middle of the drawing routine for the bunker draw. So the yellow fill area, I want to try and break into that. So I'm moving my player by pitching the ball over towards, I hope, one of the bunkers. Let's exit, and it's drawing again now. It hit the breakpoint, you see, so I just exited from the machine code monitor. There we go. We're really near two of the bunkers. Fantastic. So let's save a snapshot so that we can restore back to this point if necessary. Close to bunkers, right. Save all of the disk images and ROMs and stuff that are attached just to make sure, so that we can return back to this point later on. Yeah, they're definitely all checked. Good. Okay. Now if I go to the top-down view, and then let's go back to the 3D view. Okay, there's beginning of the render. Let's begin to understand by trying to look at the memory accesses along with the disassembly that we have so far. So we've got clear screen, render all green, render all brown, render all yellow, render all brown again, tree calculation, draw trees, draw T markers. So we're really starting to understand the high level structure of this code now, the logic of it, right? Which is good because we need to understand the high level logic of the code to be able to more easily understand the underlying data that drives how this code behaves. So this is the drawing routine. So we'll add a label here for the number of polygons. I think that this is the number of polygons because that's the number of times that it loops through and draws green areas for this hole, right? So that is a tentative label name there of the number of polygons. This value came from somewhere else in memory, right? It was stored into by being copied into from somewhere else, of course. So we'll need to find out that, but I have a feeling that it's from the memory location C554, right? And this 0-page memory location here, 45 in hex, I think it's the working value for the number of polygons, like the index of the polygon data. I have a feeling that this game is drawing lines for n-sided polygons, like triangles, squares, etc., pentagons. So I think that it's doing an n-sided line draw for the polygon, then filling it in. Yeah. Okay. And then the render all brown seems to look. It's doing a different render, right? So because the vertical surface, if you like, of the brown earth around the bunker is recessed into the ground. It looks like it was continuously rendering the brown lines, like, you know, one under each other vertically with a vertical offset. So it looks like it was drawing it a few times with different vertical offsets to get this brown shape there. And I think that then it's going to fill in with a yellow color, and then the yellow fill is going to be using a different outline, right? So that the front lip, the front edge of the bunker will look different to the visible back edge of the bunker, which is a cool way of doing it. I think it's a really good way of generating this 3D view anyway. The render all yellow, this seems to be rendering the bunker edges, right? And then rendering the yellow frames around it and then filling it with yellow. Yeah, look, see? So it's doing that several times. It's doing that loop a good few times of doing this brown line draw and then doing a yellow line draw and then filling it with yellow for the sand. Yeah, so that's how that draw works. That's how the bunker draw works anyway, the sand traps. Interesting to note that when the top view is rendering, look, it's reusing the draw fill routines, but it's just not reusing the top level render loop, but it's reusing the polygon, the filled polygon draw routines and stuff like that, which makes sense, right? It's drawing lines, 2D lines on a screen which are transformed from 3D points, of course, and then it's just filling it. So you want to reuse those routines because it's just drawing lines and filling lines with color. So the routines lend themselves very well to being reused. It's just the top level calculation which is not being reused so much. That routine at 31BF on the top down view drew a green outline, right? And then the next routine is fill with color green. So we'll just add a suitable label at 31BF as well for draw, I think draw green outline, right? This is part of the main rendering draw for the polygon stuff. So we'll just put a sensible label in there. I think this is the top down view rendering routines, right? Rather than the 3D behind the golfer view rendering routine. And now we have some high-level structure of the code understood. I want to go now and have a look at the level data in memory. So the level data from the file start address that we verified was C554. We have these bytes here at the beginning. Like I was thinking before when I was looking at this data, maybe numbers of things or types of things, followed by data tables of low and high addresses and stuff like that. So let's have a little look. If I poke in a value at the very beginning of the file of 1, and then go back to the 3D view, oh look, there's no green areas, but there's a vertical brown line. Ah, look, there's only the tee area, the teeing off area, rather than the rest of the fairway blobs. And the green blob as well. So all of the green blobs, apart from the first one, are not rendering. And that's by changing the first value from a 4, from a, what was it, 6 maybe, a 4 or something, to a 1. Okay, so let's change it to 2. Let's go to the top down view. Ah, now we've got 2 green blobs. Okay, well this is getting somewhere. So initially this hole has, you know, the green, the fairway, and then the tee area. Now we've just got part of the fairway and the tee area, right? So these are the differences that we can see straight away by editing one byte in memory. Okay. So maybe let's change it back to 5 and then go back to the main game 3D view. And then there we go. We can see all of the fairway blobs now and the green area. Let's go back to, there we go, that's what it looks like now. So we'll change it back to, should we change it? Well, we've got a value of 3 as well, right, in the next memory location. So let's change that. And look, we've removed some of the bunkers. Okay, so C555 seems to be the number of bunker blobs, bunker polygons, right? So instead of 3, there's now 1 because I put a 1 in C555. Okay. So the beginning of the level, the beginning of the whole file, basically, seems to be number of green bits followed by number of yellow bits or polygons, right? So we'll note that down. Number of green areas, number of yellow areas, brackets, bunkers, sand traps, whatever you want to call them. I'm going to go by their colours, I think, because it's probably easier to remember and easier to understand. The third byte I wonder what the third byte does. Well, this hole doesn't have any water, but it's probably going to be water, right? I'm guessing. 5 4 5 5 5 6 5 7 had a number in it, and I've just changed it to a different number. I don't notice anything visually different so far. Nothing in the top-down view, nothing in the 3D view. I don't notice any obvious differences yet in the 3D view anyway, in the course view, in the whole view. Don't see any differences. I don't notice anything different in the 3D view. I mean, the bunkers have disappeared, but that's because I already set those bunkers to be 1 rather than 3, right? So it's 3, C557. Let's set it to 4. Again, that's what it was before. I think it was. Let's check for differences, visual differences in the core, in the whole. No differences there in the rendered view. Let's change it back to 1 again. And it's rendering, and I don't see any differences compared to the screenshot that I took. Let's change it back to 4. There's another value there after the 4 as well. I wonder what that is. Poking values into memory and looking for things that change on the visually change is one way of doing this. Another way is to use the code and to see what code accesses these memory locations. So we can do that as well, I think. I don't see any really obvious differences. Has that view changed? I don't know. Marginally, perhaps. What's changed about it? Let's put it back to what it was. 5 4 5 5 5 6 5 7 5 8 5 9. Okay. 5A. Let's change that to 1. Let's go to the top-down view. Back again. Okay. Not getting too many changes that I can notice at the moment. Let's put it back to what it was, I think. Let's see what code accesses the first byte of the whole level data. Aha. Okay, so the previous, oh look, load indirect fb, y, which is pointing to C554, because that's where the memory watch point is, and it's storing that into the number of polygons. Okay, and then it's doing the number of polygons working calculation, then it's doing probably 3D transformation, I'm guessing, because that wasn't the line draw, it wasn't the fill routine, it's doing other stuff. So I'm guessing it's doing cat 3D transformation calculation and maybe perspective and then transforming to 2D screen coordinates or something like that. There's probably a few routines which do that, but look, it's storing into the number of polygons and storing into the number of polygons working. That's lucky that they're using the same areas in memory for the same thing, so that our label names highlight kind of like the structure of the code, right? That's why we use label names, is that we don't need to remember the hex values for the memory addresses and what they do. We can look at the label names and understand a little bit more about the structure of the code. So look, this is reading, well, it's read the number of polygons, or it's read the number of green areas, right, at C554. Then it's indexing into FBFC, which is at C59D, and it's reading 4 bytes of data from C59D. and it's storing those 4 bytes of data into temporary working area 21A5, 21A6, A7, and A8. And then it's JSRing off to somewhere, and then it's reading another 2 bytes and storing that into FB and FC, but it's getting it from FDFE. Okay, so we're getting somewhere. We can see from the structure of this code, it's getting 4 bytes, storing it somewhere. Doing a JSR, which probably calculates the value into FDFE, right? I'm guessing that that's what that routine does at 21FB. We'll check that in a minute. But yeah, it reads from C59D, 4 bytes. Right, so that needs to get put into the debugging notes text file. And then I think it's loading a memory address, right? That's going to be interesting to look at. So we'll put that in the memory debugging notes text file, right? Just so that we don't forget, because this is important information to remember. And then FDFE, so 21FB, probably calculated the value into FDFE, I'm guessing. Judging by the structure of this code, that makes sense. And it's reading a low byte, high byte memory address value from C55D, right? So it's reading the data table at C55D, and then it's processing more data from that area of memory. Okay, so we also need to note that down into the debugging notes text file. Stepping through, the next polygon seems to be reading from, let's have a look, C5A1, which is the 4 bytes after. So it's reading 4 bytes for the first polygon, and then the second polygon reads the next 4 bytes in memory. These 4 bytes are probably going to be, I don't know, 2 16-bit values, I'm guessing, maybe, possibly, we'll see. So we'll put that in the debugging notes text file as well. Going back to the driving range from the complicated hole, it's still the same memory address, is C59D. So even the driving range, which has a lot simpler layout, it still seems to be reading for the first green polygon area. It seems to be reading those same 4 bytes as well. So the data structure for the whole is a little bit consistent. Even if it's a more complicated one or a simpler whole like the driving range, it still seems to have roughly the same memory addresses that it's reading these 4 bytes from, and those 2 byte values, which is probably looking like, well, it's memory address offsets, right? Or memory addresses, rather, memory address table. So yeah, there's some consistency here between the files, which is very useful to know. It means that they're not completely packed. They have a bit of wasted space, if you like, or a bit of padding space, which makes it easier to parse slightly. So at the beginning of the tree calculation, we know that C55C is accessed. Let's change. Well, it's currently 2D, right? Because it read it from C55C, which contains value of 2D. Let's change the accumulator register to equal 1. So now when it's trying to process the trees, oh, look, it's only rendered 1 tree. Okay, so yeah, that's the number of trees, right? C55C is the number of trees, definitely, because the tree calculation routine picks up that value and then uses that for its internal calculation. So that's useful to know. It means that we can put that in, or document that as the number of trees. If I don't know, let's try modifying that value of at C55C, right, back to what it was, and then we get the number of trees back again. Well, it's rereading it, right, because I only changed the accumulator. So let's change the accumulator to be 5 now, and look, it's rendered 5 trees. Okay. So setting the register, like the accumulator value, after it's loaded it from memory is useful because it means that you can still observe changes in the code and how it executes without changing the underlying level data. Let's change that to 40, which is 64. Oh, look, I've got extra kind of like pseudo randomly placed trees. That's probably because they're accessing memory which hasn't been set to specific values, so just whatever is lying around in memory is being used as tree coordinates there, I'm guessing. So anyway, that looks like the number of trees, right, at C55C. Interesting to note. So that's another byte, I think, understood in the level data, so we'll put that in the debugging notes text file. Let's go back to the complicated whole data now, the one with the bunkers and all of the trees and everything. Let's just change that to C55C down to 1. Let's see what that draws, right, when we go back to the top-down view, I think. And the top-down view renders 1 tree. Magic. Okay. Back here again. Look, there are no trees, because the only remaining tree, I think, is behind us at the T. Or behind the T, rather. Strange place for a tree, but okay. Let's change this to be 10 in hex trees, which is 16 trees. And there we go. It's starting to draw the trees that are behind the T area and leading up to the fairway. Okay, very cool. Just now, C59D was being accessed as those 4 bytes when it was drawing green areas. So if I now set those to 0, look, and go back to the top-down view, the T has disappeared. Ah, okay. I don't think 4 values is enough to completely describe the T area in terms of a polygon, but maybe it's an offset. Let's try changing the values back again to what they were. So 4 values, right, is 2 16-bit values. Look, the T has come back again. Okay, so let's change maybe 1 byte out of these 4 bytes to see what visual difference we get. What should we change it to? Let's get rid of the 9D and just change it to 0. We'll just change 1 byte out of those 4 bytes which are being accessed during the rendering, and oh look, the T's disappeared again. That's strange. Okay, why has it disappeared? Let's load the snapshot back again so we have correct level data. Let's, I don't know, what should we do? Yeah, that's the correct level data. 0, 2, 9E, and 0. So, what should we do with this data? It's definitely loading these 4 bytes before it renders a green blob, right? So C5A1 was the next one along, right? The next green area, the next green blob polygon area, right? So let's, no, C5A1 is the next 4 bytes along after C59D. So if we can't understand what happens for the T area, then we can try and understand what happens for the green blob area, right? So let's add, the T area seems to have moved all the way up there, and then the green area seems to have, or the fairway area seems to have moved off somewhere, or it's not rendering. And that one, I changed it to 0. It can't be scale values, right? No. But I copied the position for the second polygon into the first polygon, you see. So the T area moved up to where the green area is, and oh look, now the green area has swapped over with the T's position. Ah, okay, so these do look like positions, right? Because I've swapped over the T polygon for the first part of the fairway polygon. So it seems to be kind of like it. We definitely seem to have swap piece coordinates, right? Okay, let's load again the old data, right? Now everything's back to normal, right? Now we're starting to understand what those 4 bytes mean, I think. A little bit of experimentation left to do. So C590, let's change this to be, well, okay, so A and 2. We'll just change those 2 bytes Ah, look, the T has shifted over a few pixels, just only a couple of pixels. But then again, it's the overhead view, right? Hmm. Yeah, it's shifting over. Okay. And 3A, it's shifted over more. So that seems to be the X position offset for the first green polygon, which is the T area. Let's change this to be a larger second number. It's moved it all the way over there. Okay, let's change that to 2, maybe? Maybe 20 was too large. Let's change it to 1A. It's moved, but imperceptibly. Okay, so let's change it to 0 and go back. Okay, let's change that to 0, 0. Go back, go back. Not rendering. Okay, not rendering. Why is that not rendering? Well, if it's at the origin, if that's on the far left-hand edge, it might be too far off the screen. Might be running into clipping issues, maybe. You see, the default value for that is 0 and 2 in the X position, right? So, okay, so let's change that to be 20. And then it's moved it off a little bit to the right. Okay, and then 20, and then 3. Okay. Ah, yeah, low byte, high byte. Okay. So if I change it to 2, the T area should be back to the left. Yes, good. And if I change it to be 20 and, let's see, 20 and 1 perhaps? No, let's change what we think is going to be the low byte. Go back. Yes, it's moved again. The T area at the beginning of the overhead view. Okay, so let's change this next value. We're doing incremental changes here to try and understand the number range, because I think this is a 16-bit value. Right, so we'll add that to the debugging notes text file. If that's the X position for the first polygon, then this is going to be the X position for the second polygon, right? Overhead. Yep, there we go. The second part of the second green polygon area, the first part of the fairway, basically, has now moved to the right. And that's the low byte of the X position of that second polygon that I just changed there. Yes. Let's change it to 60. It should move to the right a bit more. It has. Fantastic. So we'll add that to the debugging notes text file. Let's change the byte after it, which is what I think is the high byte. We'll change it to be, well, it is 2, right? So let's change it to 1, and the fairway should appear to the left. It does. That has, yes, that explains the number range then. Ah, well, there we go. Now it's moved all the way to the left, practically. Cool. Okay, so using this information, I think that we can safely say that we can move around the polygon pieces by changing their offsets. So it looks like low, high byte order for XY position for these pieces. Let's change the Y coordinate for that second polygon piece. There we go. That's at 0, 3, or 3, 0, 0, rather. Let's change it to 4, 0, 0. Yep, there we go. It's moved northwards. Let's move it to 5, 0, 0. Yes, it's moved northwards even more. So yes, X and Y, 16-bit values in memory for each piece for the whole. Loading a different chorus now, and this hole here has water as well as sand traps. I'm betting that one of those bytes at the beginning of the level data file, the whole data, is the number of pieces of water. So let's change C55C to be 1, first of all. C55C should be the number of trees, right? So C554, C555, we understand. C556 is 1. C557, let's change that to 0 from 4, right? Just moving my ball around in this more complicated hole. Guess who forgot to save a snapshot when loading that new hole with the water in it? Me. So I need to go back and start that debugging of the water drawing information now from the start again. So the hole with the water, render all yellow. Actually, the label name is not entirely correct because it's going to render blue areas, right? Okay. So the label name is not correct for the behavior that it's doing. That's kind of fine. We can fix that up later on. It's more important to understand how it is drawing blue. Now that yellow bounding area there, I think, is as it's drawing the area, but it's going to fill it in with blue, which indicates water. So I think it's reusing code, right? I think it's reusing the bunker sand trap code to render the water areas, because practically it's the same thing, right? It's got the earth vertical banks around it, and then it's got the yellow area or the blue area. So I think it's practically reusing most of the code, just with a slightly different input value. Taking a little detour into what looks like the tree calculation, it loads the number of trees from C55C, right? I'm trying to understand the beginning of the level data in memory. And after loading the number of trees and finding out that there's more than one tree, it is setting up the address C900 into FB and FC in 0 page, which kind of indicates to me that the start of the tree data is inside the level data still, but it is at C900. And the routine, after it sets up the address C900, then starts reading bytes from there and what looks like copying bytes from the level data at C900 to other areas in memory at BB92, BC52, BD12 there, and BDD2, X. And it's reading 4 bytes. 4 bytes, 2 lots of 2 bytes or 2 lots of 16 bits. I'm guessing that that's X and Y position information for each tree. We can test that. Let's set up 2 trees. So C55C now contains the value of 2. Then let's put in what we think are going to be X and Y coordinates into that memory location, right? So it's C900. Let's put in different X and Y coordinates. So we'll put 1, 1 and 1, 1. And then we need another pair of 16-bit values. So 2, 2, 2, 2. Okay? 2 different coordinates. One at 101 and 101, and then the other one at 202 and 202 in hex, of course. So let's see what we get. We should see 2 distinct trees on the overhead view. Who wants to take a bet about that's what we're going to see when we press T? Overhead view, 2 trees. Magic. Fantastic. 2 trees at 2 different coordinates. Cool. Okay. So let's take a screenshot and let's go to the 3D view. Now we'll change the coordinates, what we think of the coordinates. We'll change that to be, well, that's going to be quite a large coordinate. We'll change the low byte rather than the high byte, because I think 41 in that as the high byte would have been far too much of a change, right? We'll change the low byte there. If it's a 16-bit value, it will only shift a little bit rather than a lot. And there we go. If we compare it with the screen grab from the previous version, look, the tree has moved across to the right, and then the other tree has moved as well. And that tree has moved to the right as well. So that's the previous screen grab on the right, you see, and then the new render is on the left in the C64 view. So yeah, that's cool. We can move trees in the X position. And I'm guessing that the other one's the Y position, because that's where those coordinates kind of match up to, right? So, fantastic. We can edit tree positions in the level hole data. So let's tidy up the debugging notes text file. We still need to find out where the water is stored. I'm thinking that it's the next byte, but we need to verify that properly. So let's create 3 trees. Okay, so set that to 3. And then the third coordinate, we're going to set to somewhere else. We want it to be somewhere up there. So we're going to use the same x coordinate as the last tree, but we're going to shift it further up north, hopefully, by using a larger 16-bit value for the y coordinate there. So it should be twice the distance going upwards, right? So this is the separation between the different tree coordinates, right? So let's see, we should get a tree above the last tree that we placed. Kind of like near the bunkers, perhaps, near the top of the fairway. We'll see what the coordinate range is. Hey, there we go. There's the third tree. Wow, fantastic. We have trees. So look, the third tree is pretty much where I predicted that it was going to be based on the coordinate system so far. So that's cool, right? So back to the polygon draw calculation routine. After reading those 4 bytes for the x and y offset for the polygon, the coarse piece, if you like, it reads 2 bytes from these values here. These values, look, they're low and high bytes of memory addresses: C600, C600, C613, C626, C62F, C63C. I'm swapping the low and high bytes around to make the memory addresses easier to understand as I read them out. And that tells me that there's chunks of memory here that it's referencing with a memory address table, and it's storing those into, of course, a 0-page memory locations for indirected memory address access later on. So let's note down those values. C6, right, and then C6, and then what were they? C613, C626. Let's just copy it, and then let's swap over the bytes as I'm putting them into the debugging notes text file. Just going by the code structure and the logic of the code, and how large the separation, the deltas are between these memory addresses, it looks like could be polygon structure data, right? So we need to understand how this data is being accessed, and we need to understand the format of the data, obviously, but I'm betting, just purely based on inspection and logic, that it's going to be polygon data. So we have the first 2 pieces use the same memory address, and then we have the third whole piece, the coarse data, the third polygon using a different memory address, right? So this one is the deltas are the differences between the memory addresses, right? We've got 8 plus 3, 8, 9, 10, 11, is it? So there are how many different values here? Okay, so those last C600 values, those ones are probably just empty data. So we can probably ignore those. I'm looking for different memory addresses, right? So what is the... Maybe we have 8 pieces for the first block of memory and then 3 pieces for the next block of memory. 8 plus 3 is 8, 9, 10, 11 in decimal, right? Not in hex. So how many different values there do we have in the memory table? Looked like it was 11 different values, right? Well, let's calculate the delta values between these memory addresses first of all. First one is, well, the second to the third is 13, and that's 13 as well. 2F to 26 in hex is... sorry, 26 to 13 is, yeah, 13. And then 2F to 26 is obviously not hex 13 bytes. It is gonna be C62F minus C6. No, not 13. C6 26. Typo. C62F minus C6 26, right, equals 9 in hex or decimal, same value, right. So, okay, so that's 9 bytes difference compared to 13 bytes in hex, 16, 17, 18, 19 bytes in decimal. Okay, the next delta is D. Okay. The next one along is C649, C63C is D bytes. Okay. So the delta difference between these memory addresses is not the same. Okay, so let's have a look at the first reference block of memory, because this code seems to be copying over n numbers of values based on the first value in the memory block, right? Is that what it's doing? That's what it seems to be doing. Yeah, this code here, as I step through it, it seems to be using the first byte from that polygon, that assumed polygon data, and then looping and reading in 2 bytes for each n value that is the first byte in that assumed polygon data. So maybe it's reading 2 bytes for each as a count for each of those values. So maybe this polygon data is storing pairs of bytes, n numbers of pairs of bytes. That would work out, right? Because if this value is 9, 2 times 9 is 18 plus 1 byte gives 19, which is 13 in hex. Yes, that works out. So it's n numbers of pairs of bytes. That's the structure of this part of memory for the polygon data. And it also seems to be then reading those pairs of bytes and doing BPL checks, branch on plus or negative, basically. Plus is 0, or all the way up to 7F, and minus is 80 because it's got the high bit set, right? 2's complement mathematics, binary mathematics. Yeah, pondering this more, it does seem that this is, yeah, the number of points followed by pairs of bytes for those points. I mean, they're thinking about it logically, right? BPL checking if a byte is positive or negative twice implies that you're doing a coordinate check with signed byte values. Okay, that's the only kind of like the most likely logical explanation I can think of. And if they are signed byte values in pairs and it's n numbers of them, then it's polygon. So we'll add this assumption at the moment to the debugging notes text file. The code was doing plus and minus checks and also doing adds and subs. So because it's doing adds and subs, I think it's offsets, perhaps coordinate offsets. So let's go back to the driving range because it's simpler level data, and then let's try and edit this by using memory editing in the machine code monitor. So that's the start of the driving range data. There's only 2 polygons. There's only a certain number of trees. So let's begin to edit that. Let's, what should we do? We'll change the number of polygons first. I think probably get rid of the number of trees as well, right? We don't want any trees. We want to remove the trees. It makes it quicker to render, but it also makes it easier to understand if we're going to be debugging into the code again. right? We don't want to be debugging into the tree rendering routine. We just want to understand the polygon routine. So let's set that to 1 polygon. Go back to the top-down view. Yep, 1 polygon. Okay, fantastic. And look, the flag has changed position as well. It's no longer in the middle of the second fairway piece. Okay, I wonder what the flag position does. Okay, well, we'll see. Maybe it's the origin for the last piece drawn. Maybe that might be it. Yeah, maybe the origin for the second piece is in the middle of the top of the part. Yeah, I don't know. We'll check that probably. Anyway, polygon rendering, right? 1 polygon. Okay, 1 polygon. Top-down view, definitely 1 polygon. Thank you. All right, now let's apply what we know or what we think we found out and put in the debugging notes text file, right? So let's have a look. These should be the coordinate offsets for the first piece. So C59D, we will change the coordinate of the first piece, the X coordinate of the first piece, and look, we've got clipping issues, rendering issues. It's probably because the line draw has completely got stepped over, and that's probably because the first piece, the first T area, probably has a negative offset. So we'll just move it along. There we go. So that trapezoid probably goes into negative space, and that probably messes up the game's arithmetic. So we'll change the X position to be something sensible. We can change the Y position offset for that piece to also be something sensible, and it should move up there. There we go. It's moved up. Fantastic. So that's our understanding of the polygon offset position calculation. The level data for that's understood. Now I think that's pretty much validated. Now let's check where it's pulling the polygon information from. Well, it's pulling it from C600. Okay, so let's try and change the shape of the T, the first polygon piece. Let's change that shape, shall we? So we'll just update the debugging notes text file so it's a little bit tidier, because we've validated that that's what that means now. So we'll put that better understanding now back into the debugging notes text file. Right. So piece addresses, right? These are piece addresses, or the addresses of each polygon. The polygons can be n-sided, right? So it's a 6-sided polygon with these coordinates. Or maybe offsets, I think probably offsets, but we'll see if they're coordinates first, and then we'll see what we get. So let's change that to a 4-sided polygon. Go back to the top-down view. There we go. We have a 4-sided polygon. Let's change it to 5 sides. A 5-sided polygon now. Yes. Okay. And before it was 6. So let's change it back to 6. Go back to the 3D view, back to the overhead view. There we go, back to a 6-sided polygon. Fantastic. Okay. So let's see if we can make this a triangle, and we can. Wow. Okay. So we definitely know that that's the number of points, right? Let's see if we can understand the coordinate base of these polygon definitions now. So the polygon definitions, okay, so low byte, high byte, low byte, high byte, low byte, high byte. That's what we're guessing, right? Here and here. And then the third one, low byte, high byte. Those last two are negative. Okay, so the BPL check, that branch on plus check, will fail, and it will go into the negative handling code, negative number handling code, right? So the signed value changes. Okay, so let's see. It might be relative coordinates looking at this, because don't forget the code was doing plus and minus checks and doing adds and subs and things like that, and different accumulations. So let's see. Can we make a triangle with different coordinates. So we're starting at 0, 0, and then we'll do a relative move to the right, but not up, and then we'll move nothing to the right, and then we'll move up vertically, okay? So we'll move across with a unit of 4, 0, and then we'll move up vertically with a unit of 6, 0, okay? So we should have a triangle which goes up like that. Let's go to the 3D view. So it's tried to render the triangle, but it's not filled it. So the fill routine has probably failed, and maybe the line draw routine has failed. Okay, so if it's relative coordinates, right? Maybe we should make this a negative value so that it is able to fill the triangle, or maybe let's move across a little bit more. If we move across, yeah, look, the top right hand corner has tried to shift over to the right, but I think it's unable to fill the triangle for whatever reason. So let's try making that a negative number so that it should be underneath. There we go. We now have a triangle which reflects the coordinates that we are using, and it's relative coordinates by the looks of this. So if I change that back to 0, we should have a right angled triangle. There we go. We've got a right angled triangle. Fantastic. So yes, relative coordinates, signed 8-bit values, bytes basically, for the polygon data. Let's just update the debugging notes text file to reflect these findings. Just wondering, this starting coordinate, it might be a starting relative coordinate rather than, yeah, there we go. It's not drawing a line from where the flag is. But look, the flag is at the origin of the piece, but the start of the triangle has shifted across by this relative amount. That's useful to know, isn't it? That means that we can place the flag anywhere that we like within the last piece of the green area, the fairway that gets rendered. Fantastic. So that's how you can understand how to draw the hole, the fairway, the tee, the green area. I wonder where the gradients come from. That might be something that might not be in the level file. We'll see. Let's change it so we have two identical polygons, basically point to the same polygon data for the first and second piece. But let's have the second piece at a different offset, okay, different coordinate offset by changing. So let's change the number of triangles, or two pieces now. Instead of one piece, we have two polygons. And we need to, there we go, we've got the two triangles, but we can change the position of the second triangle. Notice where the flag is. The flag is relative to the last piece. So that's cool. Right? I think with this that we can really start to edit the level data. We can almost edit the whole thing, right? Let's check C555. I think that this should be the bunker, so we'll check it, change it to be 1 bunker. And where's that bunker is, we're going to make it point to the same triangular polygon as before, right? So the offset is at C5BD, right? And these are the offsets. So we need to make sure that we have a sensible X and Y position offset for the triangle. So we'll put it somewhere. We'll put it somewhere different. There we go. That should be a good enough coordinate, I think, maybe, for the bunker. That's for the piece offsets, of course. That's where we documented it before from inspecting how the code works and looking at the memory and testing that, right? So what else do we need to do? We need to make sure, yes, 656D is pointing to C600. So that triangle that we've created, that polygon piece that we created, it's pointing to the same polygon piece, but it's going to be rendering it hopefully with yellow. There we go. It's rendered it with yellow. So we can put bunkers where we like now, and we can define bunkers as any polygon shape that we like. We're using a triangle, but we could make it other things, right? That's fantastic as well. So actually it means that this game has the concept of creating shaped polygons and then drawing those shaped polygons with different colors, right? The bunker color, the yellow color, the water color, I think. 6554, 6555, 6556 is being accessed, and it's being accessed by this routine, which reads and stores into the number of polygons again. So yeah, 6556 is probably the water drawing routine, right? Oh, the C556, sorry, is probably going to be the number of water polygons. Right, so let's see. Yeah, and that's reading the offset data from C5DD, right? So when it reads, yeah, 65C5DD, different offset data, BCD. Yeah, so each chunk of offset bytes is 20 in hex bytes. The delta between them is 20 bytes in hex, 32 bytes in decimal. That kind of makes sense. 32 divided by 2, 16 divided by 2, 8. So yeah, that's probably a maximum number of 8 pieces for each type. Based on the coordinate differences. Yes, okay, so we've probably got a maximum of 8 green pieces, 8 sand trap bunker pieces, and 8 water pieces for each hole. Okay. Before we render it, let's make sure that we've got sensible offsets in there. We don't, so let's put some sensible offsets for that next polygon piece. I think it's going to be the water, but we just need to make sure that it's the water, so we'll use the X position as over on the right and the Y position not so far up. And then let's see what we get in terms of rendered output, right? I mean, this is going through the calculation part of the data, so it's C57D, right? So those are the memory addresses for the polygon offsets. So we need to make sure that those also point to the polygon that we created at C600. So let's do that as well. The default values seem to be C600 anyway, which helps us because it means that we don't need to explicitly set them. So that's good. So let's see what we get when we render. Right. Let's go to the top view. We've hit a breakpoint. What do we have? We don't have water being drawn. We've got the bunker being drawn. Let's just double check the memory. We've got correct offsets, or what we think are correct offsets at C5DD. Let's check the start of the level data. In memory, oh yeah, okay, so we've got 2 polygons, 1 polygon, 0 polygons. Whoops. That should be a different number of polygons, right? We need to have water polygons, what we think are going to be water polygons. So C556, let's change that to be 1 polygon. Now, when we exit, when we go to the top-down view, we should now see, there we go, there's the water polygon, there's the polygon that I was expecting. So we've got the 2 green polygons for the fairway, for the grass. We've got the 1 yellow polygon as expected, and we've got the 1 blue polygon for the water. So yeah, I think that pretty much means that we've understood practically, is it nearly all the bytes in the level data now? So let's put a ranged watch load breakpoint on the memory addresses that we don't fully understand yet. C558, C5. Well, we know what C55C is, but let's just trap the code which accesses it anyway. So we're going to be trapping the code now which accesses these other memory locations. We'll go back to the 3D view. We'll hop over that. So that's okay. That was checking the number of trees, right? Look, there's a BPL check. And an EOR and a store. Okay, that's C55B. Okay, you know what that's telling me, right? If it's reading C55B, which is in the level data, and if it is doing a BPL check, that's doing a signed byte check again, and I think that that's probably indicating it's going to be a coordinate. Maybe X coordinate offset, maybe Y coordinate offset. or something. Logically speaking, it's probably going to be a translation offset, translation coordinate offset for the entire course. I think, judging by the level data structure and the code, how it's structured and how it's accessing it, I think it's going to be that, but we'll need to check that probably properly. Apologies for the noise in the background. The renovation team for the house behind have started up again. Great. So yeah, there were BPL checks, negative checks, and it does a subtract. Okay, so C55A and C55B. So I think it might be an offset based on the logic of the previous code, right? The logic of the previous code tells me that that's what that's going to be doing. So let's I think we need to take a screen grab, right, of the completed render for the top-down view, and then we can compare against that because we can then tweak the memory values, right? I think that's what we shall probably do. Let's delete the breakpoints. Let's change what's at C55B and C55A, right? So that's what it is by default. That's what we should have from its default values of A and 0. So let's take a screen grab. And then we'll compare against that later on. So let's change those memory locations now. And we'll change that to be... What value should we use? 1? Is that going to be too small? Maybe? Let's go back. Has it changed? It's a bit difficult to say. It's very difficult to say. Let's make it a larger value. Let's change it to be, I don't know, 4 0 is probably too big. 3F might be too big. I don't know. It's a bit difficult to tell what the number range is going to be without understanding the maths behind it, right? Let's bring back, let's go back to the top-down view. Something has definitely changed, right? Let's go back to the screen grab. Let's do a comparison. Look, the triangles have altered their position with respect to the flag. That's interesting. The flag offset has changed. The triangles are... Oh, well, I was changing the Y position, wasn't I? Yeah. I think that was a Y position change. It was the second value, right? Maybe we need to... Maybe an X position, maybe a Y position. Let's just make the value a lot different. Let's go back. Let's just check. What is it going to be? Yeah, so let's go back to the top-down view. Okay. Yeah, so that was what it was previously. So it's an X translation. Okay. So, okay. So let's change that value there to be, I don't know, 81, 80, 80 is a very large value, right? Maybe it's not. Maybe the maths has wrapped around. So that it has moved, right? It definitely has moved. The little flashing dot is where we are, apparently. Okay, so let's change that to be 0 again. And what do we get now? Now it's A and 0. That's basically back to what it was before. Okay, and now let's change that to be A and, or 3A and 0. Let's see what we get now. back again. And interesting. Maybe I'm changing it to be a completely unrealistic coordinate. Yeah. Maybe the maths is just going completely crazy or something. But yeah, the pieces have definitely shifted, right, with respect to the flag. So it looks like it's a whole course offset, right? So one of them seems to be the X course, or the whole offset in the X and the Y coordinate base. And the flag doesn't seem to be affected by that. That's a strange coding design choice, isn't it? So that it seems to be moving them up and down depending on if they're signed or not as well, does it? Yeah. So that's what it is currently with the data. Let's change the value and then let's compare. Okay. I think if I use too much of a large number, I think the maths goes and wraps around. I think that's probably what we're saying. But yeah, definitely this seems to be translating the whole course around, but the whole without the flag. Okay. So, green polygons, sand traps, water polygons. This number here, so 54, 55, 56, 57, C557. What is this going to be? Well, C557 hasn't been documented yet. So let's see what loads C557, shall we? Let's go to the top-down view. Nothing touches it. The 3D view does touch it. And what is this going to be? It's doing something with the value, but what is it doing with the value? What else could it be? Well, it's certainly starting to load and starting to run quite a lot of code dependent on that value which was in C557. Let's make sure we change it back to 1, how it was before. C557 equal to 1. Yep, there we go. Now let's see what changes we can see on the screen. So let's grab the whole screen. Is it the tree, maybe? Is it the tree type? It is not the tree type. The tree looks the same. Okay. I've got one tree now in the level, and it's not changing the tree type because the tree looks identical. Is there anything else in the screen that's changing when I change that number from a 1 to a 2? Is there anything that you can see on the screen? Let's change it to a 3. It's not the tree type. Well, let's change it back to 4 from what it was at the start of the level, and nothing visually has changed in the top-down view or the 3D view. Let's change it to 5, and again, nothing has changed in the tree view or the top-down view. It's the par for the core for the whole. Look, changing it back to the 3D view re-renders the par. There we go. It's the par for the whole. Oh gosh, it wasn't in the actual top-down view or the 3D view itself. It was just the par number for the whole. Gosh, okay, how funny. So let's tidy up the debugging notes text file. I think that means that practically all of the bytes in the level data file, at least the bytes at the beginning, and plus all of the polygon data, the bunkers, the water, the tree positional data, all of that kind of stuff has now been documented and understood, I think, which is fantastic, right? So now we can use all of this newfound knowledge that we can tidy up now. We can say that I think that's unused as well, because those ones weren't weren't breaking, they weren't coming up on a watch load breakpoint, right? So I think that we can safely say that we've understood practically all of the level data, and we can probably, if we wanted to, but I'm not gonna, hand edit or create a level editor for this leaderboard course data. So let's just tidy up this debugging notes text file, and then I will commit it to GitHub. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Take care, have a great day, evening or night, wherever you are.